July 15th, and we just got going with recording a virtual star party. So let's show you where we got a scope that's already set up, and we are actually up in the north looking at an object called the Owl Nebula. This is a planetary nebula. We pull up our first image. We actually had it's all zoomed in. We did a 2-minute image with our ZWO ASI 294, and you can see it. We actually got it looks like a satellite came by as we were imaging the Owl Nebula, and this is you can see it actually has some color to it. It's kind of a greenish color. We'll zoom right in, and you can see by the two eyes on there that it kind of looks why it's called the Owl Nebula, because it's got those two big eyes on it. Up in the Big Dipper. Nearby is another object. What we'll do is we will zoom near that one. I'm going to zoom over here to the big Messier object nearby called M109. There's a bunch of Messier objects over here, so we'll do that. That's a galaxy, so let me bring over to M109. We'll find it. That's nearby. Oh, M09. Let's try M109. Find it. Okay. And now what we're going to do is we're going to slew over to it. It won't take long to get there. So the telescope is going to slew over to M109. This is the Celestron C14. We're there. All right, so we're back. And we're heading to the next object. So this object is NGC 4214 in Canis Venatici. It's a small dwarf barred irregular galaxy. It's about 10 million light years away, and it's part of the M94 group, which is also part of the Virgo supercluster. We'll zoom in a little bit and look at it. It's kind of interesting because it's irregular. It's not elliptical or spiral. It's kind of made its own way in this world as an irregular galaxy, and you can see it kind of looks weird. It's not. It has no definite shape. That's its name, irregular galaxy. In our virtual star party, we're going to M64. This is the Black Eye Galaxy. So I'll set up the software. We will take a 2-minute image. I'll tell you a little bit about the Black Eye Galaxy. Now, if you're viewing through a telescope, you don't need to wait for an image to appear, but because we're going to wait for an image to appear, I'll tell you all about this place. So, this is in Coma Berenices. It's also called the Evil Eye Galaxy, and it's part of the Messier collection, M64. And it's about 17 million light years away, and discovered by Edward Pigott in March of 1779, and then independently by Johann Bode in the same year. So it's interesting that year they were all looking all over the place. And then later on, Charles Messier was looking for it. He found it a year later. So, or looking in that area and found it a year later. What's interesting about this is it has a dark band of absorbing dust in front of the galaxy's bright nucleus, and it makes it look like you got a shiner at the bottom of your eye. You can imagine the galaxy's like an eye. You got a big black spot right in the bottom of a very bright part of the galaxy. So it's pretty well known because of its appearance in even a small telescope. So we're just a few seconds away. I will be back as soon as the image develops. All right, we're back. We got an image, really nice image, looks like, of the Black Eye Galaxy. And this would be pretty much what you'd see through a low-power eyepiece through a modest telescope. You can actually see a little dark area here at the galaxy, but what we can do with this software is we can kind of zoom in. We could take a look at it.
Oh, very nice.
And I haven't even done much with pumping up what our resolution is here. This could be a pretty nice looking object. if I don't screw it up. Try it again. Let me go back out here. Let me do that. Try that again. All right. So I brightened it up quite a bit so we can see some of the rings around. So I can zoom way in. We can actually see some structure in the rings around here. But because you can see this big dust cloud here blocking the nucleus coming at us. So it's kind of above the galaxy. If we're kind of looking down at an angle towards the surface of that galaxy, you can actually see a little more detail in the rings. And this is kind of what you'd see. I mean, that's a really high power eyepiece, that you would see if I'm doing it this way. But because we're taking images, we can, this is a single image. If you were actually doing imaging, you would take multiple images and stack them up, and you could get a really nice image of the Black Eye Galaxy.
How long was that?
That was 2 minutes.
It's a lot of,
with the hyperstar.
a lot of photons.
So this is a hyperstar capturing at f2. It'd be a whole different ball game in its native f10 or f11. So that's why we're taking advantage of this. All right. So let's see what else we can look for over here. There's another couple of things nearby here. Try, is Virgo down? Let's see where M87 is. If it's too far now, we won't bother, but let's see where it is. Yeah, that's close. What do you think? You think we can get to M87 from here?
Oh
Yeah?
yeah. That's a couple degrees away, right?
Yeah. All right. So we'll slow down to M87. We don't have a hard limit on this, do we?
It's pretty low, but
Yeah.
just looking at
All right, so we'll capture a 2-minute image of M87. And while it's capturing, I'll tell you a little bit about it. So this is a pretty famous recently. It's also known as Virgo A. It's a supergiant elliptical galaxy in Virgo, and it's one of the most massive galaxies in the local universe. It has a large population of globular clusters. So if you imagine the globular clusters in the Milky Way, we have probably about 150 to 200 in the Milky Way. This galaxy has over 12,000.
wow.
Yeah, just ridiculous amount of globular cluster, which kind of contributes to being why it's so massive.
How did they figure that out?
You got to have some really good telescopes. But what's even more interesting about this galaxy is a jet of plasma originates at the core and extends about 4,900 light years out into space at about a 30-degree angle as we see it coming out towards us. And it's traveling at relativistic speed. So when I say relativistic, that means it's close to the speed of light. That is very, very fast for matter to be traveling. And it's one of the brightest radio sources in the sky. So it's a popular target for both amateur and professionals. So if you remember last year, the famous Event Horizon telescope with all these telescopes all over the world that were imaging, they were imaging M87, the black hole in the center of it. You maybe remember that the orange and yellow image of that black hole. They just followed that jet down to the center of where the galaxy was and imaged the light bending around the center of that galaxy. So you're not actually seeing the black hole, but you're seeing where the hole is because light is bending around it. Very cool at the black hole image. So we're about 5 seconds away, and hopefully we get a nice image of M87, one of the most massive galaxies in our local universe. And here it is.
Crank it up, you might be able to catch a little bit of the jets.
Yeah.
Maybe not.
I thought we had jets on this before last time when we were looking at it again.
Yeah, I don't know if we did a 2-minute or 1 minute.
This was a 2-minute exposure. Oops, that's not helping. Let me do it auto.
Does it not track or you think it's pulling a line up? Or just needs balancing or something?
I
So
don't know.
M87. So we're not getting as good an
Sometimes you
image as
get
I've seen.
Good tracking. Then
On,
sometimes it'll be elliptical like that.
On some images, actually there it is.
Yeah.
Over here is the jet. This is the jet that we were talking about. That's 4,900 light years away from the center of this, traveling at relativistic speed. You shot out of the top of that galaxy. Pretty amazing that we could actually capture it with our telescope, our imaging. That's the jet. That's the jet right here. That's pretty cool. That's just one exposure. If we were to stack this up, we might even get some color out of that jet.
Oh, yeah.
And the galaxy itself.
I shot this before.
So this is but this would be under pretty good power in a telescope to see that image like that. In a regular scope, this is probably what you see. You could probably still make out that jet in a wide field. And so medium high power, you'd probably see that. Or high power, you'd see that. Pretty cool. Pretty cool. All right, I'll pause this until we figure out what our next object is. All right, we're back here. We've flipped the scope to the other side of the horizon, or the other side of the meridian. Takes a couple minutes to do that. We focused in on a place called the Lagoon Nebula, way down south. And then we'll work our way up from there. And took a 2-minute exposure. So here's our exposure. Well, not tracking great. But here's the lagoon.
That is amazing.
That's not too bad.
Even for bad tracking, it's not bad looking.
Oops. Let me try that again.
Yeah, I like the idea of not tracking. I heard, like, just another thing to screw around with.
Well, that's the lagoon, and you can actually see the pink color in there. It's a star-forming area. Let me tell you a little bit about it. It's one of two that are really big that we could see in the northern hemisphere. So lagoon, it's also known as Messier 8 or M8. It's an interstellar dust cloud in Sagittarius. It's classified as an emission nebula. So discovered by Giovanni Chioderne before 1654, and is one of the, like I said, the two star-forming nebula visible to the naked eye from mid-northern latitudes. And the Great Orion Nebula is the other one, visible as a winter one. Well, this is a summer one. You can actually see it with binoculars, and it appears as a distinct oval cloud-like patch. But with a telescope, you can actually see what we see here. You can see the dark lane in there, and you can see this little bright spot down here. If I can zoom in. That's the hourglass. Now, we didn't track well, but this is shaped like an hourglass, so it's one of the features that you look for in the lagoon if you're able to see it through a telescope. It's within the nebula is an open cluster. That's this group of stars here. The stars formed out of that nebula. It's estimated to be about 4,000 to 6,000 light years away from Earth, with dimensions of about 110 long, so that's up or down this way, about 110 light years this way, and about 50 light years this way across. So I say light years very, it seems like a small number when I say 110 or 50, but that's a big number when you're talking light years. And like many nebula, it appears pink within time exposure colors. But if you were to look at this through your eye, through an eyepiece, it would just be gray. You'd see the detail there, but it would be gray. What's interesting about seeing the color with the camera is you could actually see the kind of like reflections in areas of light bouncing off of different clouds. It almost gives it a three-dimensional look. There's actually, on a really good still night, you can see globules in here. There's some globules here you might see, and then over here, we didn't track well, so we didn't capture them, but those are just like very dense globs of matter where solar systems are probably forming right now. But pretty interesting place. That's M8.
How
And
many light years away did you say?
what did I say? Did I say how far it was? It's 4,000 to 6,000 light years away.
Okay, well, so the closest galaxy we looked at last night, in comparison, was 10 million.
10 million.
That was the closest.
Yeah, that's a long ways away. So right above this, with a telescope, you really only have to tip the scope up a little bit, and it's almost, if you had a big enough eyepiece, you almost think you could see it in the same field of view, but you can't, is M20, which is the, no, I'm going to go to M20. we'll slew to that. There we go. It wasn't listening to me. You see how far that scope slewed? That's easy for me to say.
Like this.
Didn't go far at all.
Not far at all.
Not far at all. So we'll take a 2-minute image, and when we get back, we will talk about what is going on with the M20.
Right.
All right, so we're back. We've taken exposure of M20, and there's the auto focus of it. You could actually see color. I didn't like that. Let me go back a little bit.
It looked like it tracked a little bit better.
It did track a little bit better. You could see color very clearly there already. You can see the reflection nebula here, and the reflection nebula here is blue, and the emission nebula is red. And this dark lane is why it's the trifid. It looks like 3 pieces. There's a piece here, piece here, piece here. It's divided into 3 pieces. I'll zoom in a little bit. And this does it no justice of what you could do with imaging, but through an eyepiece you would struggle to see color here. You would have to really have really good sensitive eyes to see color here. I don't see color when I look at it. The dark lane, I can see all the, all this stuff going on here, but and even in between. But I don't see color when I look at this through an eyepiece. And you can see there's a lot of stars in the background of this because it's right in between us and in the core of the Milky Way. M20, the
So
Trifid
that
Nebula.
first star near the center, is that a double?
It looks like, I don't know if
Because
that's,
all the rest are round.
yeah, that might be 2 stars there.
I think it is.
It looks like 2
That's
stars.
Yeah, I think it is, yeah.
But look, you can actually see the reflection of light coming off of these globules here. Look at that. And this is all in our way. Probably these stars are illuminating this, so there's shadows coming at us. Gives you a real 3D effect, doesn't it?
That's pretty.
That's pretty.
Now that you can't do with a telescope, like zoom in like I just did. That's kind of cool to do.
Yeah, all I see is gray. The Orion Nebula, I swear I can see green. And I know there's blue and red, but
Yeah.
I get the perception of the green part of that nebula.
Oh, no kid.
Yep.
Yeah.
I don't know why.
Interesting. Everybody has different color sensitivities. All right. So while we're here, might as well check out check out the nose.
Oh yeah, the nose.
The nose.
Nose nebula.
I've always known it as the swan, and Dave has convinced me that it is the nose. So we're going to go to the nose. Once you see the nose, you don't unsee the nose. So here we are. We're at the Swan Nebula, or the Omega Nebula. We'll take a 2-minute exposure. I'll tell you a little more about it when we get back. All right, so our image has developed 2 minutes later. And here is the Swan Nebula. If you're looking at, this is the floor of the water here. This would be the body of the swan. Here's his neck and his head. All right. Now I'll show you the nose. This is the nostril.
Oh, Jesus.
There's a nostril, and there's the bridge of the nose. And there's the
God
nostril. Now, forever, it will be the nose nebula.
It does.
I can't even see a swan anymore.
Yep, it's a nose. It's a nose peeking at you through space now. And now
I
you
have to rotate the camera.
I
make
told
that
you,
one.
yeah.
Yeah, that's all you can do.
It's because this rotation is a perfect nose.
Yeah, the biggest.
So
big
now that
nose
we've
of all.
ruined everybody's life,
Yeah, it does kind of look like a swan.
the Swan
Swan
Nebula.
nose.
And we're picking up a lot of stuff here. Now this one, I don't see any color if I'm looking through a telescope. But you can pick up all this dust around here. It's better to pick this stuff up if you use a filter. You can't get all of this.
That's really extensive.
Yeah, it's pretty extensive. If we were to take longer images, 5-10 minute images, we could. It's all out here. And this is actually just a dark cloud here. You can actually see pieces of it over here, creeps in over here, over there. That's a dark cloud that gives it its shape. Otherwise, this would be a lot like looking at the Orion Nebula sideways. The Orion Nebula was facing us. It was turned 90 degrees. You can imagine that's like the edge of the Orion Nebula.
It's tracking better and better the farther.
Yeah, I
north
think
we
the
go.
farther north we go, the better it tracks. All right, so let me pause this. When we're down here, might as well, let's look for the Eagle Nebula. I'll show you where we'll find it. It's actually very close by.
Yeah, you can't loosen the clutches enough to get a good balance.
Yeah, I tried
You
last
could
night.
put 10 pounds on the end, and it's still.
It's still
So
fine.
we'll be
yeah.
back shortly. All right, we are back now after our exposure of the Eagle Nebula. This may be familiar when I zoom into to you if you were a fan of Hubble images. This didn't track great. It's kind of hit and miss. But these are the towers of creation, kind of rotated 90 degrees, but there's one here, here, and here. And they are being eroded by stars up at the top of them, pushing away all that stuff so they create these towers of dust and gas. And you may recognize the Hubble image had it's an incredible image of the towers of creation.
You know, the scary Opus is shooting better than Hubble now.
We are imaging, and we're just a moment away from, oh, this is much better we got the other night.
Yeah, I'm not even sure we were on it the other night.
There we go. Actually got some nice color in the Ring Nebula. Now, when I look at this through my eyepiece on my telescope, I don't see that green. Some people see it, I don't. But I see the ring, and I'll see a little shadow across the middle, and then if I got a high power eyepiece, I can see that little dot in the middle of the central star, which was the star that it was really the whole star that shed off all these layers and is now sending ultraviolet rays out there, exciting the electrons in the oxygen and carbon atoms out there. And as electrons release that energy, it releases it in green and blue. And that's what we're seeing is that green and blue. And you actually can see a little red on the outside too from hydrogen doing the same thing. But one of the fairly close planetary nebula. What were you saying, Bob?
You can see the central star.
Yeah, you can see the star there. You definitely see
Tracking
this.
was terrible.
Yeah, so tracking's not great, but you can see the central star in the middle there. So this is about 2,500 light years away. One of the closer planetary nebula, and in a little while we'll go to one that's about half as far away. That's the Dumbbell Nebula. We'll go to that in a little while. But we've had a request to head over to a supernova remnant, and that's what we'll do next. I'm going to pause this, and we'll head over to the Veil Nebula. So we'll be back shortly when we get to... All right. Okay, so we have imaged the Veil Nebula, and sometimes when it's not a very good night, that's what you see, nothing there. But what we can do is we can find a little detail out of this, and we might be a little south of it. I don't see it there. I thought maybe this was the star we were looking for. But that doesn't look good, does it?
Let's see. Oh, that's the star, though, isn't it?
I don't know if that's the star. I just kind of clicked a spot. So let me try this again. I'm going to pause our recording here. Okay, so we've got our 2-minute image back of the western edge of a supernova remnant. So you can see the star. That's between us, between us and the supernova remnant. And there's this leading edge here, basically coming from the top of the screen down towards this way, of dust and gas being expelled or in the way of the shock wave of this supernova remnant, supernova. And so this is called the witch's broom, and it's called that because you kind of have a thin handle, crooked handle up here, and you got little wisps down here that you would use to sweep the floor with, if you can imagine, or the back end of it. If you could zoom in, it almost looks like this is... I think, Dave, you were talking about this. It's almost like a vortex.
It's like a vortex. It does.
Spinning
Like water
around
going
and makes
down.
that.
Yeah.
So that's
I
pretty
never
amazing.
noticed that until just now.
The witch's broom. And this is what you'd see in the eyepiece without color. The eyepiece, you don't see that much color, but you do see color when you image this. And you get a lot more color the longer you image. But you can see it just like this in an eyepice with a modest telescope.
20 inches.
The 20-inch scope, you'd see that.
Yeah,
It's even better than that.
that's the best I've ever seen. Is that 20
Yeah.
inches? It's beautiful.
It's pretty amazing.
Yep.
But this is our 14-inch SCT doing at f1.9, doing a nice job. So what we'll do now is we'll go to the other side of the supernova remnant. We'll slew over to here. This is what is this? I'm gonna put my glasses on so I can read it. 6992. So that's what we'll do. Go to 6992. First we'll find it. See, I'd like to get a little more of this on here. So can I move it over here? And maybe get all of it that way? I will try that.
Try that.
So we're going to slew, so like I want to see this edge over here because this is really interesting to talk about. So that's where we're at. I'm going to pause this and we'll start. All right, we are just about done with an image from the eastern edge. We're on the western edge now. And in about 5 seconds, we should see an image of the eastern side. And there it is.
Wow.
Oh, it's a good thing I moved it. Good.
Wow.
So there's the eastern side of the Veil Nebula. Very nice color on this. But as I said on the other side, through a telescope you won't see that, but this quick image, we can actually see the color on here. And this is the front of the eastern edge. I see here, let me see if I can't pull out a little detail here. Oh, I like that on my way too. Hang on. Well, that's even worse. How to Make a Good Image Terrible by Mark Winrich. Let me see here. What did he say?
Nice focus.
Yeah, did you guys focus it tonight?
Yeah.
Nice job.
Where'd it go? I know it's there. We just saw it.
Huh. It's gone.
There it is. That's about the best I'm going to get. But over here, and it actually continues further over to the right of the picture here. There's more to see. But I see like 2 lines here and here that come down. And through a larger scope, it actually looks like a waterfall kind of coming down, or like a pair of fangs coming down from the edge there. That's what really defines the eastern side for me. That little, it's almost like wrapping around as it's flying away. So pretty cool. So you want to see Pickering's triangle? We'll try that. It's in the middle. It's right in between these two, and I'll show you where it is on this map. So this is where we were, where the dot is, and before we were over here. Now we're going to go over here. So I'm going to put us here. Over there, and we'll slew over there, and we'll do a quick image of this. And we'll be back to talk about it in a minute. Okay, so we're back, and we went in between the two. So this is the whole supernova remnant here. We looked at one side, and we looked at this side, and now we're looking at this little piece here called Pickering's triangle. Took a 2-minute exposure, and you can see very faintly this looks like a little slice of pizza here. Pickering's triangle. And what I did to adjust this was I used this little tool here, and I zoomed in and out on the curve, and I'm able to adjust it a little more finely on the curve. So I was adjusting on the edge of this curve here. So that's Pickering's triangle. As you can see, it's really faint here. I have never seen this through a telescope, so it's cool to see it this way. Actually, I should say I did see it at Cherry Springs through somebody else's scope. I saw it. But
Could you make out the triangle?
you can make out the triangle. Actually, it could make it up better than this. And it was all gray and shadows. There wasn't any color to it whatsoever.
Could you expose it longer?
Yeah, you definitely could. You want to try that?
Yeah.
You want to try that? Yeah, we got
3
time.
or 4 minutes maybe.
All right, so let me pause our recording here. So here we are back. We did a 3-minute exposure, which is about 50% longer than the one we just did of Pickering's triangle to see if we can get more detail. We might have gotten a little more detail. There's a little blue more in here. Picked up a little more stuff out there, but it's still not. Let me see if I can tease a little more out of that.
There you go.
Yeah.
Just teasing a little bit more out of it. I might be pushing it there. So there's a little bit more there.
I can see a triangle.
Yeah. How did these guys see this back in the day? I don't know how they saw that stuff. They had terrible equipment.
How were they? How were
Really
they,
dark shadows.
how were they at the turn of the last century getting spectra of all those stars?
That's amazing. That's probably easier to get than this kind of a detail.
God almighty.
Let me pause this. All right, so we're at the Garnet Star, and it's definitely red. I think when we looked at this before, we had enough clouds or stuff in the sky.
We had like a
We
area
had
desert.
like a halo that was reddish. It actually accentuated the color. But it's because it's so clear. It's very bright. Maybe I take a shorter image. This is a 10-second image. We take a 2-second image. See what that looks like. Should come right up. Well, not much different. It's very red, but it's also very bright. So. It was more interesting when it was hazy.
So through an eyepiece, that would look pretty spectacular.
It would look very red. It would look incredibly red. But I think we're just blowing it out. Let me try to do a short one. We'll do like a half a second. Let's try that. Maybe it'll appear redder and not blow out the image.
And I think that's just the sensitivity of the camera.
Yep.
Doesn't look like a deep dark red.
No. But this is where visually and the telescope are going to be very different. Visually, this would be very, very red. And here you can kind of see it's reddish, but because it's so intensely bright, the pixels in the camera are making it look whiter than it would.
What's the magnitude of this star?
Good question.
And is this a red giant or is this just a?
This is a red giant. Magnitude is 4.23. So I'll give you what information I have on this star. It's a red supergiant in Cepheus. It appears garnet red and is located at the edge of a nebula, actually. And since 1943, the spectrum of the star has served as the M2 standard by which other stars are classified. So it's visually nearly 100,000 times brighter than the sun, with an absolute magnitude of -7.6. It's also one of the largest known stars, with a radius of about 1,000 times that of the sun. So if it were placed where the sun is in our solar system, it would engulf the orbit of Mars and possibly Jupiter.
Good God.
It's a variable star, and its apparent brightness varies erratically between 3.4 and 5.1. And it's got a whole bunch of different periods that have been reported, but they are consistently near 860 days or 4,400 days. So it's a erratic variable star at the same time. Monster. Just a big star.
That is big.
And I highly recommend that you look at that through an eyepiece. That's very, very red. All right. So now that we're up here, let me see where this object is. This is one I wanted to see tonight. NGC 7331. Nearby. All right, so let's slew over there. This is a galaxy, and it's very near a couple of other galaxies. It's called the Deerlich group that's up there, and if you're much of an astronomer, it's also near a group called the Stephan's Quintet. So what we'll do tonight is we'll take a 2-minute image of this. We should be able to see multiple galaxies here. So I'll start the image and then start recording. I hope I started recording. Am I recording? I am recording. All right. This is NGC 7331. And I like this area because there's a whole bunch of galaxies here. This is a really pretty galaxy. You can actually see, it almost looks like a whirlpool of galaxy here. Little dark lanes over here. You can see some arms coming off of it. And this is one, if you got time to take a long image of it, it's a very, very pretty galaxy. Fairly close compared to these other ones. So let me tell you a little bit about this galaxy first, and I'll talk about the ones around it. It's an unbarred spiral. It's about 40 million light years away in Pegasus. It was discovered by William Herschel in 1784, and it's the brightest member of the 7331 group of galaxies. The other members, and you can see them around them. So there's 1, 2, 3, 4, 5. All those galaxies are over 300 million light years away. Just ridiculous distance, and you can actually see these through a pretty. You'd need a pretty good sized telescope. So I have a 14-inch telescope. I can pick up these galaxies pretty easily, and the fact that I can see something that's 300 million years old is pretty amazing. I mean, that goes back to dinosaur age for us. So the core it seems to be slightly off center. So it's hard for me to tell with this image if it's off center. And one side of the disk appears to extend further away from the core than the opposite side, but that's maybe you can't see that. It's a little farther out here than it is out there. Sometimes it's considered the Milky Way's twin, but at one point was considered that way. But since the early 2000s, we've known that the Milky Way has a barred center, and we're a barred spiral. So this is not a barred galaxy, and hence it's lost its Milky Way twin moniker. What's also interesting about this is that in most spiral galaxies, the central bulge typically rotates with the rest of the disk, but the bulge in this galaxy rotates the opposite way as the rest of the disk.
Okay.
No kidding. So hard to figure out why that would be, other than something flipped or it collided with something, but it does rotate the opposite direction. So these little galaxies over here are over 300 million light years away. And if we imaged longer, let me see, we're going to compare this image to what we're looking at here in space. So let me do this. So I'm going to blow this up. I'm going to move this over here and put those back up here and see if we actually captured Stephan's quintet in our image. Put this up here. And I'll bring this back over here. And there it is. I see it. All right, so way down here, see this down here? I'm going to blow it up. We did capture Stephan's quintet. Mm-hmm. So there are 5 galaxies here. 1, 2, 3, 4, 5. And this is a really popular area for amateur astronomers to image. Those 5 galaxies are, all but one are related. This one right here is much closer than these 4. And through a telescope, these 2 really only appear like one galaxy. It's hard to decipher them. But that's Stephan's quintet. Pretty cool, huh? We actually captured that. Very difficult to see through a telescope. That's definitely something you need to image. Even my 14-inch, I struggle to see this. But when I saw the field of view of this, I said, oh, maybe we have it in here. But that is definitely Stephan's quintet. All those galaxies. So we just looked at 5, we probably looked at 10 galaxies in this one image.
Yeah, there's galaxies surrounding the big one there.
There's all kinds of galaxies. Those are the ones that were 300 million light years away. All that's the Deerlick group.
There's one to the lower left as well.
Down over where?
I don't know if you zoom in.
Over here?
Yeah, there it is.
Yeah. Let's see what that one is. So that's over here. Yeah, you don't get a lot of data on this other than where it is and what in the sky. But that's pretty cool. We actually got to see the Stephan's quintet, probably a dozen galaxies all in one image here tonight. That's kind of cool. Yeah, like that. All right, we'll pause and we'll figure out our next.
I've done that with long exposure, and you can see a whole pile of galaxies.
There's a whole loads of galaxies up there. We're in Pegasus now, so let's. Since we're in Pegasus, I know there's a planetary that's very blue in Pegasus. Let's see if we can find it. I may have to look it up and then find it. So blue snowball. Oops.
Oh, it's gonna be super tiny, right? We can zoom in on it.
Diameter on it, and to balance it, you just went to balance, and it had to play hell with the motor. And you watch the current drain on each direction, and once the current was, but shit, you could just hear it. Oh.
And you're like, oh, it's destroying itself.
Oh yeah.
It would destroy itself till it got to where it would balance.
But we do have an ammeter. It's up there in the shelf if we wanted to.
So basically, you're looking for the minimum, right? You're looking for a minimum amount of current draw.
Yeah.
And that's your balance.
And it should
All right,
be.
there's a 60-second exposure.
Where the hell is it?
What the hell?
Oh,
is
there
that
it is.
All right, let me start recording again here. All right, so we did a shorter exposure because we weren't tracking right of the blue snowball, and you can actually see it's pretty blue.
It is blue.
And it would look an even deeper blue. It's actually a little blown out here. Let me try to get a little more contrast. There you go. That's more like it. It's pretty much what you'd see through a telescope. It's really pretty cool to see. So there it is in your low power eyepiece, but that's much bluer. Right here, it's much bluer in your eyepiece than that. You're kind of getting the effect of the pixels being filled up here, oversaturated. But that's the blue snowball, another planetary nebula. More traditionally, how planetary nebulas look as they putting on distance glasses to read, but that doesn't work. Let's try that. Actually, I don't think I have that on my list here, but that's kind of cool. Blue snowball up in Pegasus.
So that's just a star similar to our own.
Yep. So
blown off its shell.
So our star, in about 4 billion years, will be shedding off layers of its outer layers. The sun will start contracting and expanding, and as it expands and then contracts, it'll leave those layers out in space, and eventually it will collapse into a white dwarf, and that white dwarf will be, emitting radiation, and the ultraviolet wavelength will be exciting the oxygen and carbon atoms, electrons, into higher orbits, and as those electrons go back into their lower orbits, they'll release energy, and that energy happens to be in the blue and green color, and that's what we see when we're looking at these planetary nebula, dying stars that are exciting the shells of gas around them, and the fact that they're colorful is a bonus for us. Pretty cool. What else is up here? We're up in Andromeda. We could look at Andromeda. Let's take a look at Andromeda. M31. We've stayed up.
High enough field, it should be pretty good actually.
We stayed up late enough to find Andromeda. So there it is. We will slew over. This we don't have to take a long image of, so I won't even pause this. Once it gets there, and we're there. Oops, I won't pause this. I will take a quick 1 minute exposure, and we'll get Andromeda. And Andromeda is a beautiful galaxy, especially to image, but it can be beautiful to observe as well. You'll see 3 galaxies in the image that, hopefully we'll see 3 galaxies in the image that we'll get. This is our closest neighbor. It's a little under 2.5 million light years away. Very, very close. And we didn't even know it was a galaxy until somebody was measuring a star in that galaxy, and being a variable star, and we had one nearby, and the ship that they were shifted so much, you could tell how far away they were coming from. For it to be 2.5 million light years away, where the other one was, a handful of light years away, made it apparent that that was not a nebula. That was another galaxy entirely.
When I was a kid in high school, we always called the Andromeda Nebula.
Yep, everybody did. It was
Everybody
fairly recent.
I don't know when they first.
Wow.
First.
So there's Andromeda, and actually I'm kind of zoomed in, so I'll zoom back out. So there are 3 galaxies here. There's one big one in the middle. There's a little one over here. This is M31, Messier 31. This is Messier 32, and way over here is Messier 110. And this is about what you'd see through an eyepiece. I can't, it's probably a little wider field than what you see in an eyepiece, but that's about what you'd see. And you can actually catch dark lanes here. I will enhance them in a minute, but you can actually catch dark lanes here, and that's a good measure of how good you're seeing is how much of those dark lanes you can see in Andromeda during that time of year. So in the summertime, you got to stay up till almost 1 in the morning to catch it, like we are right now. But in the fall, it's a beautiful object, and at dusk, great thing to look for this fall. So I'm going to attempt to bring out more detail in here, something that you'd see with an image of Andromeda. I'm not getting more detail, I'm getting more contrast. You can kind of make out some dark lanes around here. This is an object that really needs multiple exposures, and you stack them up. I've actually taken multiple exposures of this galaxy with this camera, and you got a real nice image out of it.
Actually, yeah, you showed me. That. It's beautiful.
So, but that's about what you'd see through a telescope. I don't want to exaggerate what you're going to see. It's kind of a virtual star party, but through a telescope, that's what you'd see. And everybody's seen these beautiful images of Andromeda. That's pretty good through a telescope to see that beautiful, beautiful spiral galaxy. Details on the dark lanes and such.
Now that's not a bird spiral, right?
No, that's a true spiral. True spiral, and will likely be eating up the Milky Way in a few billion years when the 2 galaxies merge. It's more massive than the Milky Way, so we will be the loser of that eating contest. All right, be back with the next object. Actually, I'm gonna stop. Star party. We just moved to M15, a globular cluster. We hadn't seen any globular clusters yet, so I thought it might be time to look for one. And this one's in Pegasus. And so globular clusters are just these groups of stars that all form together. They tend to be very, very old. In fact, this one, I think, is estimated about 12 billion years old. So that is a very, very old cluster. It's a magnitude 6.2 globular cluster in Pegasus, so it's pretty visible with most telescopes. Discovered in 1746 and included in Messier's catalog of comet-like objects. It's about 33,000 light years from Earth and 175 light years in diameter. It has an absolute magnitude of minus 9.2, which makes it very luminous. Makes it 360,000 times that of the Sun. and it's one of the most densely packed globular clusters known in the Milky Way. And its core has undergone a contraction known as core collapse. It has a central density group of stars that may be surrounding a black hole. It's home to over 100,000 stars, and it's notable for containing a large number of variable stars, 112 variable stars and 8 pulsars. It also contains a planetary nebula that was discovered in a cluster in 1928 called Peas 1. And I know that a lot of amateur photographers try to find Peas 1. It's not easy to find. We're certainly not going to find it in our image.
How did a guy in 1928 find a planetary?
I don't know. It takes a lot of talent to do that. But I will comment that you're seeing a globular cluster, and it really is it doesn't do it justice, because these things through an eyepiece. I highly encourage you, if you get an opportunity to look through a telescope, to look at a few globular clusters, and this is a good one as well. And it's almost three-dimensional when you look at them, because they are globes of stars, and you can kind of focus in and out of that globe and different parts of it and see it. And to an extent, you can see it here. You can see these bright stars out here are closer than the stuff in the middle, that core that's out there. That is a very, very pretty cluster, M15.
I almost like it better than M13.
Yeah, this I've kind of zoomed in here, so this would be like a high power. If you were looking through a low power eyepiece, wide field, it would look like that. But
they're my favorite object.
They're beautiful,
Yeah.
Absolutely stunning. First time I showed my mother one, I showed her M13, and I told her before she looked, I said, "You see this? It's going to look like diamonds on velvet." And she never forgot that from that point on, because it really does look like that on a really good night.
The coolest thing I saw years ago at NEAF, Teleview had a display where you'd just look through one of their telescopes, and they had a piece of like black velvet, and I don't know what they sprayed it with to make it adhere, but they took a piece of aluminum in a fine file
And
he
sprinkled
filed
it on
and
there.
they sprinkled on, and you look through that telescope, and it looked so freaking much like a globular cluster.
Oh, that's cool.
It looked just like you can
That's
see in the
really
night
cool.
sky.
Yeah.
Absolutely black, and these little tiny glittering.
No kidding.
That's awesome.
Absolutely
That's
beautiful.
awesome. All right, I'm going to pause us.
I never heard of such a thing.
Well, everything else I have here is kind of all over the place.
Teenage
So.
kids. Well, they're probably out of high school by now.
You guys want to take a look at Jupiter?
Might as well.
Call it a night. Jupiter's right at the meridian. Let's see if it'll slew one way or the other. All right, it's gonna go the short way.
I shot Jupiter through the brew house last week and a half ago, something like that. Came out alright.
So how long of a shot do you think we need of Jupiter?
1,000th of a second, because it's clearer tonight. And I would put it on continuous.
That's a good idea.
There she goes.
Huh, the satellites lined up nice.
How many are there? 4? Even that's too long of an exposure. That's about as low as it goes, right? Oh, you can put it to 0. I don't quite understand 0.
Yeah. Nope.
So how do we manage to get?
I think we just
we turn the gain down. That's right.
it's on low.
It's on low now.
Yeah.
Well, gee, if we had turned that up, we probably would have got more detail on the triangle there.
Oh, I didn't think about that.
Must have left it there.
Yep.
That's my bad.
could use the other software and get different.
Oh, right. Yeah, that's what we did. We used the planetary version of that. Alright, yeah, so you can tweak the exposure a lot easier there. And actually get it down into the milliseconds on the exposure times. I think we're somewhere in the 100 millisecond range. Maybe a little less. What are we at there? Zoom in a little. A little more. And crank it down to like maybe 50 millis. Still too much.
Am I taking image? There it is.
There we go. 1600 microseconds. Look at that. 700. That's less than a millisecond, and now we're good. We're right around a milli. That's not too bad. It's not the right scope for this, obviously.
Yeah. So I'm gonna. Oh, we recorded all that. All right.
Did we?
Yep.
Okay, what did I say?
I'll know when I come back and look at it. But you got to see the whole process of going from one software to another. But that's Jupiter, and this is not the way to see Jupiter. If we continue with these virtual star parties, we'll show you Jupiter through this same scope set up at I think it's F10 or F11. F11, and you will see detail on Jupiter like you wouldn't believe. So this is good for a wider field. Definitely not good at looking at detail on planets. But there's Jupiter. You can definitely see some dark bands here. You can see different bands up on top. This is the equator. I don't see any red spot on here, but that's certain times that you can find the red spots. If I turn the exposure up a little bit, you can see 4 moons. If I turn the exposure up, you can see 4 moons. There they are. Now, I don't know which ones are, but you can actually look these up. There's actually keys to what moons are which moons are what. But these are the 4 Galilean moons. Call them Galilean moons because Galileo saw them, identified them. Very cool. Jupiter. So while we're here, let's right next door is another planet. We'll go to Saturn. Through a telescope, the first time you see Saturn, hopefully it doesn't have to go all the way around to find it. That's right, it's going back. Good. All right, so we're on Saturn. And I don't know that I stopped. I don't know that I stopped taking images, so maybe we're right on it. Yeah, we imaged all the way through that. So we will make Saturn a little less, so we could see the rings. Might be too much. Rings are nice and wide open on Saturn, so you can actually see the gap between the rings and the planet. And again, this is 1 billion miles farther than Jupiter is. Not 1 billion miles out there, but 1 billion miles beyond Jupiter is this. And we can see the rings. We can't see any detail on it. And again, you follow along with what we're doing here. We'll try to show you Saturn in another episode through F11 scope, and we'll see some detail. Maybe we'll see the split in the rings. We can see shadows on the surface of Saturn. We can see the cloud deck on Saturn. So, but it is cool to see that Saturn does have rings. It's out there, almost 2 billion miles away.
You see any satellites?
I'd have to open up the. That's something you do see in a telescope. So let me overexpose. I probably got to crank this up to. Yeah, so there's 1, 2, 3, 4 satellites there around Saturn.
Actually, zoom out a little. I think there's another one there.
There's 5. There's one here.
Okay, yep.
1, 2, 3, 4, 5. Would you see another one?
Right there, lower right.
6. So wasn't Saturn the one that got a whole bunch of new satellites? Got 79 satellites.
It's got a bunch.
So those are all moons of Saturn. One out here. It's 1, 2, 3, 4, 5, 6 satellites. I believe that one's Titan. That's the largest moon. The only moon that we know that has an atmosphere. Pretty cool. Saturn.
If I could live out there, I'd probably live on Titan, honestly.
Titan?
I just think the real estate values are better. They're going to appreciate more.
They're going to appreciate a Titan?
Yeah, it's just it's a nicer place to live.
It's pretty far away. Very rural. Very suburban.
We got a lot of lakefront property.
If you like methane lakes. All right. Well, that'll do it for this evening. Thanks for watching. All right. I'm done recording, so we can do whatever you want.
That'll be great.